Well, I think we should get started now. And what I wanted to do was to continue with the ideas of how to understand the wave mechanics as, well, fairly qualitatively. But what I think I can show you is that you can solve and understand some fairly complicated problems even with our relatively simple methods. Did I lose everything there? Oh my. Try again. Yeah, well, what I was trying to do was to show you how, if you just understand that what we're dealing with is waves, even in the case of matter, especially small particles, it turns out that they're pretty much what you would expect waves to do, and that you can get a very good insight into things that seem rather mysterious, I think, if you don't appreciate that you're dealing with waves. Namely, I'm sure you've had the course in chemistry where you were told that you have s orbitals, p orbitals, d, f, whatever, and I don't know if you appreciated where they come from. Let me try. We'll set up this thing here. Well, let me save this for later. I think I should not turn this off entirely because that seems to kill everything. So let's go back to these PowerPoints. What I was trying to tell you is that if you have the Schrodinger equation, just from the structure of it, you can sort of see what it's going to do. Let me write it down again. It has its wave-like character in that you have the second derivatives of some kind of a wave with respect to space. There's a coefficient out here which turns this term here into a kinetic energy. It's h bar squared over 2m. This part here is actually p squared. This part here turns out to be p squared over 2m. So this is a kinetic energy. And then what makes one problem different from another, kinetic energy is just if you've seen one, you've seen them all, mv squared, f mv squared. But what makes problems different one from the other is this potential energy function, which varies from problem to problem. It could be that the potential energy is 0, that it's just a ball rolling on a table. And that potential energy added to the kinetic energy gives you the total energy. Well, we'll put in this wave function again, as we had it here. We'll give you the total energy. And the way we draw the diagram is that we have something like this, a box, say, and we imagine we put a particle in with a certain amount of energy. And here in the case of a simple flat box, we can take the potential energy at the bottom is equal to 0, so there's no potential energy here except when you get to the wall. Then the potential energy becomes some large number. So you can think of a wall as being a potential barrier. I just want you to understand also a little more complicated case, namely that of where the potential is not 0 everywhere. Rather, it could be bowl-shaped, so that the potential energy, this curve here, is proportional to some displacement of half kx times a spring constant, half x squared being displacement along some direction. And if I put a ball rolling in the bottom of a bowl like this, the classic, let me say it again, we can separate it into two parts. This is the potential energy, this curve here, and the kinetic energy, let me say, is some magnitude like this at when it's moving as fast as possible. Okay, so as I go along, this would be the kinetic energy. And as I roll along, what happens is that the picture changes. I have partially potential energy here, U, this is what this curve is, so that my kinetic energy changes to this value. So it's just saying what this equation says, that the kinetic energy plus the potential energy is the energy I put in, and that is a constant. So as I just roll along in this bowl, kinetic converts to potential up until I reach this point here, for example, where the total energy is equal to the potential energy, at which point there's no kinetic energy, the ball has stopped moving, and it stops, and then it rolls back down. It converts back. So that's what these diagrams are trying to tell you. Okay, now, at the risk of being somewhat difficult, let me do something like this. H bar squared over 2m, the second psi square with respect to x squared. Let me put the u term on the other side, e minus u of x times psi. Well, let me put the psi over here to make a certain point. Oh, by the way, there's a minus sign here in front of the kinetic energy term. That comes about because, remember when we took the second derivative like a sine, it changed the cosine and it changed to minus sign, so you have to put a minus in front. So you have something like this. Now, from your calculus, you know that if you have a function of x, which will be our psi of x, the first derivative, d psi dx, is the slope of the curve. Right? This is old stuff. And the second derivative, which is of psi with respect to x squared, is the derivative of the slope then with respect to x. So that is sometimes called basically the curvature. It's telling you how fast the slope is changing. So the argument that I would like to make is that if you look at this, this quantity here is the rate of change of the slope of the wave function. So if I have a wave function psi, if this rate of change of slope is large, it would look something like this. In other words, the slope is changing very fast. Whereas something like that, the slope is changing slowly. So here you have the psi squared dx squared is small, and here it's large. Okay? And the sign is like that. If okay. Now Now here the slope is changing. See, the slope is considered positive if it's going upward, right? This is the slope. It's positive. The slope this way is negative. The rate of change of the slope, if the rate of change is negative, that means the positive slope is going more this way. If the slope, 1, 2, 3, if your slope is doing something like that, the second derivative of your slope, of the function, the derivative of the slope, if it's negative, you're doing something like this. Okay, so what I'm trying to show here is that when the energy minus u of x is greater than 0, this slope, well, the changing of the slope is such that, well, let me put the minus sign over here, like this, leaving off the constants. I'm interested now in the curvature of the thing. If the energy is greater than the potential energy, the negative of that, if that's a positive, if E is greater than u of x, then this quantity will be negative, which means that the slope is turning toward the axis. See, if E is greater than u, then this is a positive number. It's a negative number here. It says that the curvature is such that the slope is turning downward. That is to say, the curvature over the value of the function is negative. In other words, the slope here is decreasing. So what that is saying, when you really look at it, it's saying that when the energy is greater than the potential energy, which means that there is some kinetic energy. You see, this is actually the kinetic energy. The total energy minus potential energy, as I said, that's the kinetic energy. So if the kinetic energy is positive, then the wave function will turn to a decreasing slope, meaning that the wave function will go toward the axis. When you think about it, what that's telling you is that the wave will oscillate. Because whatever you do, see, in the next stage of this thing, the wave function starts here, and its curvature turns it toward the axis. And when it crosses the axis, it says the curvature wants to decrease again, and you will get an oscillating function, which means that when you have kinetic energy greater than 0, you get a wave. On the other hand, if this function this part turns negative, which classically it cannot. If the kinetic energy should be negative, if the sign is negative, a half mv squared over 2 cannot be negative. So something changes here dramatically. What happens is the curvature turns the other way. That's what I'm trying to say in this slide. Namely, if the kinetic energy is negative, that's not a physical situation. What happens is the wave function turns upward, away from the axis. So with that general idea, it's maybe a little bit much mathematically to discuss. But the point is, I want to show you, again, see, this is the curvature. And when the total energy is greater than the potential energy, that is, when the kinetic energy is positive, the curvature and the psi have the opposite sign. So when psi is greater than 0, the curvature is downward. And when psi is negative, the curvature is upward. And so the wave function is always turning toward the axis, which gives you a wave-like phenomenon. On the other hand, if kinetic energy could be negative, like for example, suppose the particle, you want to put the particle up here. It only has this much energy. Its potential energy is greater than its total energy. It would make the kinetic energy negative. So here, what happens is that the curvature turns away from the axis. So that makes it difficult for the wave function to fit in. Let me show you a case in point here. You see, here's something I started to talk about before. You have a wave traveling along, and I'm going to put it not on a flat potential, but on a potential that goes up. Not like a bowl, but more like a straight line. Now what you see is that wherever the kinetic, and this is the total energy, this is the potential energy in this particular model. This is I've chosen U being just a straight line. This author calls it V, but it should really be U because V is a potential and U is a potential energy. But okay. By the way, this is from a rather more advanced book, but you guys could understand this. Namely, that so here's the potential energy, here's the total energy. That means that the thing has all of this kinetic energy. Now, let's say it's moving this way, up the hill. It's going to be losing kinetic energy. That's the difference between here. It's less kinetic, slower, till it reaches where the total energy is equal to the potential energy. This is the total energy. Where that happens, the particle should bounce off because it's rolled up this incline, and now it loses all its kinetic energy. It's got only potential, and it should slide back down. But on the way up, you see, its curvature is always toward the axis, and you get this oscillating function like this. But when you reach this point, all the energy is potential, and if you go into the body, then the curvature wants to curve away from the axis. But it's got to curve away just so it goes to 0 at infinity. See, that's the thing. It curves away. So this explains, now I can maybe go back to the French model here. Where did we do? I think we found that in section 2. Okay. So here we have, of course, just by review, the idea that you have a certain energy, and this corresponds to a certain wavelength. This is a pretty low energy. The wavelength is long. As I raise the energy, it's all kinetic now. All kinetic. No potential. It's all flat. So but that's pretty obvious. Let's see what number 2.3 is. Okay. So here's the point. You see, when in this box, here's the total energy, here's the potential energy. This difference is the kinetic energy, and the kinetic energy is positive inside the box, in this region here. Now, the difficulty comes when I reach the wall, if the wave function is now going to curve away from the axis, as you see it doing here. So I only get a good function, and see, that's bad, because I have to be able to integrate this wave function over all space and get a finite number in order for it to be so-called normalized. You can't have a wave function which is infinite when you take it over all space, because this is a probability, and the probability should be 1 that you find it. It can't be infinite, because there's only one particle, presumably. So that's the normalization condition. But you see, if I can hit the boundary just right, such that the curve, it's still curving away from the axis. Let me, yeah, let's, ooh, see, it wants to curve away from the axis. If I go too low, it wants to curve away from the axis in the forbidden region here. But if I get it just right, it's curving away from the axis, but it's going to go to 0 at infinity. And that's a good solution. So the combination of a waviness where it has kinetic energy and a decreasing solution when it doesn't, when it has negative kinetic energy, but it has to be perfectly matched at this energy to get this decrease to go to 0. Now, somebody asked, what happens if I change the size of the box? Somebody asked in the office hour. I think I can do that, actually. They allow me to do that. If I change the size of the box, this wave no longer fits in at that energy. See, it hits the wall with a finite value, then it runs away from the wall. Then it runs away from the axis, runs away from this axis here. So if I make the box bigger, should I make the energy lower or higher to get it to fit in for this wavelength? See, the box is bigger. I need a longer wavelength. Now, a longer wavelength means a lower energy. So I should be able to get another wave function like a good one by lowering the energy a little bit. And, yeah, whoop, tricky. Okay, there you go. So because the box is bigger, the energy needed to get a good wave function is lower. And if you probably did this homework example where you had to find the energy levels, use the energy levels in a box. I don't know if you had to find it, but you had to use it. And you had these various things. And the formula for the energy of the nth level, this is level 1, 2, involved n squared, but it was also over L squared, which says that if the box gets bigger, the energies where these levels are goes down. It goes down as L squared, and that's what I'm showing here as well. Okay, so is there any question about this? I just wanted you to see that where there's kinetic energy, you get waviness, and where there's no kinetic energy, you get an exponential decay into the wall. But those have to match up. In order that the wave function be normalizable, they have to match up. If I pick any old energy, even in this box, most of the time you get bad-looking wave functions. This is very bad out here, you see. But if I there you go. See, so the wave function decreases exponentially at both sides. Because here there's no kinetic energy, but the wave, because it's a wave, is able to sort of wave its way into the barrier to a certain extent. That's the feeling I wanted you to get. Now let's go back maybe and apply that to this picture here, which is more complicated. It's not a simple box. You see, what you can figure out, now in this more advanced book, they actually derive a formula for the shape using Schrödinger's equation and this particular potential, say it's a function of z or something, and they get this thing here, which is a complicated function called the Airy function. We're not going to worry about that, but we can understand this very well. The point is that as the particle rolls up the slope, its wavelength gets longer because its speed is going down, so wavelength gets longer. Also, you'll notice the amplitude gets larger, so you get a longer wavelength, and you get a greater amplitude as you slow down. Now, classically, that makes sense too, because as a ball slows down, it spends more time in a certain space, in a certain place. Right? So, and the amplitude of the wave function tells you the probability of finding it there. So it's more probable you'll find the ball or the particle where it's going slowly. It's my own story about how you hit a tennis serve. If you throw the ball up, when it stops, it spends most time right there. And that's the place to hit it if you can. So when it's going slowly, it spends more time there. When it's speeding up, it spends less and less time in any one place. So that would be reflected in the wave function by having a higher amplitude here. So this mathematical solution is correct. Actually, I mean, I would believe the physical feeling before I believe the formula, frankly, because it has to make sense. So our physical feeling is that as we roll up a hill, the ball goes slower and slower, the particle goes slower and slower, the wavelength gets longer and longer, and it gets more amplitude because it's more likely to find the ball when it's in this place here when it's moving slowly. So that makes sense. Yes? That's right. In quantum mechanics, when it goes negative, it is allowed to do that, but it dies out. It can't really travel. It can penetrate ever so slightly. In fact, this is known as quantum mechanical tunneling. We'll actually hopefully get to that today, if I can possibly speed up. The fact is that it does leak a little bit where its kinetic energy is nominally negative, but it cannot propagate as a wave. It's forbidden to go in there, but because it's a wave, it can. That's good. You see, the oscillating or traveling part becomes exponentially decreasing when the kinetic energy is negative, nominally, where the potential energy is greater than E. There, we get this dying thing. At this wall, we get this dying exponential. Okay, so that's beautiful, and this is a rather advanced problem. Now, we can do another problem here, and let's sort of guess the answer again. Again, it's a hard problem from a more advanced text. But here, we have that same sloping potential, but now what he's done is put in a wall here. Oh, maybe I should have made the point going back. That any wave could do this. You could have energies here or here. Every wave, every energy is possible, except when the ball rolls up the hill and uses up all its kinetic energy as potential.